So in our next session, Tour de Force, Tammy and Melanie Windridge will be our guides as we tour laboratories and companies around the world to reveal the breakthroughs and gains being made. We start our journey at the National Ignition Facility in California, and with Tammy from Lawrence Livermore Laboratory. Please welcome on stage Tammy.
Valerie. Good morning. It is such a pleasure to be with you. I know many of you heard about our ignition breakthrough on December 5th of 2022, where we finally realized fusion ignition at the National Ignition Facility. In that experiment, the NIF generated more energy out of the target than was put in. And this was a goal that had been over 60 years in the making and required a team of thousands. This plot that we're showing you on the right is the NIF fusion yield, where the vertical axis is yield in megajoules over time since when we turned the laser on in about 2010. The pink horizontal line is the max laser energy that was available. And the histogram, the little bars below, show you our fusion yields over those 10, 12 years. And you can see we struggled for a little while before 2022, where we finally had a bar that exceeded that laser energy in. Now, the kind of fusion that we were doing at the NIF is called inertial confinement fusion, ICF. And we achieve fusion by creating a plasma of very high density, very high temperature for small amounts of time. And this is just one of many different fusion approaches. Many of them probably more familiar to you than others. The sun, for example, is able to achieve fusion via gravitational confinement. Then there are tokamaks like ITER, JET, others all around the world that use magnetic confinement, and then lasers is something called inertial confinement. And all of these different types of fusion exist in different density, temperature, and confinement time space. This is what we call the triple product of fusion. Your density times temperature times confinement time has to be sufficient that you can hold a plasma just long enough at high enough temperatures, dense enough, that you can get those fusion reactions to occur. So gravitational confinement with the sun is very, very dense, relatively cool, 15 million degrees Celsius over a very long confinement time, 100,000 years. This is the amount of time it takes radiation to escape from the center of the sun out to the edge. Magnetic confinement, on the other hand, is a very low density plasma, very hot, 10 times hotter than the center of the sun, and we hold that plasma on the order of seconds. With inertial confinement, which I'm going to be talking about today, we're very dense, very hot, and because your density and temperature are so high, your pressures are enormous, and we can only hold the reaction together for fractions of a second, tens of picoseconds. And to do this, we use the National Ignition Facility, where we're building our own miniature sun. The NIF is located at Lawrence Livermore National Lab, about 50 miles east of San Francisco. And NIF is the world's largest and most energetic laser, which enables us to study these very extreme conditions in a regime of physics that we call high energy density science. Now, the NIF, as you can see, is the size of 3 American football fields side by side in a building 10 stories tall. It actually isn't just one laser, but houses 192 separate beams, each one alone one of the most energetic in the world, combined to give us an energy of 2 megajoules. In terms of power, which is energy per unit time, it is 500 terawatts. So this is actually 1,000 times the power of the entire US electrical grid. But of course, the reason the lights don't flicker across the globe every time we take a shot is because it's that huge amount of energy compressed in just nanoseconds. And then for the laser nerds out there, this means it is a frequency tripled neodymium glass laser at a wavelength of 351 nanometers. It is UV light. And if I take the roof off the facility to give you a look inside, you can see that most of this ginormous building is filled with hundreds, thousands of large-scale optics. And the lasers bounce back and forth across the building before they're focused down on that little not little, very large target chamber at the end, 10 meters in diameter, that sits right in the middle, a little target. So up at the top right, this is our canister that we call a hole ROM. We're gonna shine our lasers into that canister. And right in the middle and the bottom right is the fuel pellet of deuterium tritium that starts out at about 2 millimeters in diameter. So what we're doing, of course, is using inertial confinement fusion to bring star power to Earth. But whereas the sun is 1 million miles across, the star that we're going to generate in the lab is about 2/1000ths of an inch, half the diameter of a human hair. So let me take you inside the facility now to give you a closer look. Let's zoom inside, and we're going to start at the master oscillator room, where the little pulse of laser light starts out at 1,000 times less energy than a typical laser pointer. It gets split 192 ways, bounces back and forth, passing through hundreds of large-scale optics, getting amplified up by absorbing more photons of the same color. And as the laser bounces back and forth, it gets amplified 1,000,000 billion times up in energy. The lasers all get sent towards the target chamber. Half come in from the top, half through the bottom. They shine down on that hole ROM. The lasers enter that hole ROM and irradiate the inside walls to create a bath of very intense X-rays. And the X-rays then compress and heat that fuel pellet until it becomes that tiny star. And if we do it right, we get ignition, more energy out than we put in with those lasers. Now, why is this significant? What we were able to achieve on the NIF in the last 2 years was achievement of scientific energy gain. And this is a crucial step towards the realization of the enormous potential of fusion energy. If you will allow me, we'll go through this little diagram, which is just a step deeper into the physics. Again, the laser beams come into the inside of that canister. They heat the inside wall to generate this bath of X-rays. So just like your oven at home that you're trying to fill uniformly with infrared to bake your pie, we're trying to fill the whole ROM uniformly with X-rays to start compressing that fuel capsule. Now, the next diagram over, what happens is these X-rays then very rapidly heat the surface of that capsule, blowing off that shell. And then, by conservation of momentum, it's like creating a rocket that blows off that shell. And by conservation of momentum, the rest of the capsule squeezes inward, and we simultaneously heat and compress the fuel. Now, for over 10 years on the NIF, and essentially for almost every other fusion experiment we've done on Earth today, you get the top arrow. Your burn is actually quenched before it spreads. You want this uniform compression to create this spherical little star. But instead, most of the time you get something messy and ugly looking, like that top right image. Only when we were able to achieve ignition in 2022 were we able to achieve the bottom right. We sparked a little burn right in the center of that DT fuel that could then propagate through more of the DT, giving us bootstrap heating. We got the plasma hotter and hotter. And when you get hotter and hotter, you make more fusions. And that's what gave us ignition, that more energy out than we put in. Let me give you another analogy. This is equivalent to lighting a match. And when your match quenches, the whole burn just kind of fizzles. Ignition meant that we were able to start a fusion bonfire. Now, the NIF at the moment is the only experiment in the world that has demonstrated ignition and a burning plasma, and this is a regime that is required for all fusion reactors. So that is why this is significant. This is something the whole world should herald. We've been working on it for so long. And it wasn't just a fluke. We've now achieved ignition 4 times more, 5 times total, with our most recent shot in February of this year, giving us 5.2 megajoules out for 2.2 megajoules in. This is a scientific energy gain of 2.35, so more than twice as much energy out as we now put in. And I alluded to this earlier, that fusion ignition has been a 60-year journey. The idea of inertial confinement fusion was developed before 1960, before the laser itself was invented. And as legend goes, just 2 or 3 days after the very first laser was invented, John Knuckles, who later became one of our lab directors, decided, we can probably use lasers to make fusion happen. And that set us on a journey at the Lawrence Livermore lab where we built a series of larger and larger lasers, culminating with the NIF that came on in 2009, 2010, and then we've had a steady advance of progress since then. Now, to be clear, the NIF is a scientific exploration facility. It's very different from what an inertial fusion energy power plant would look like. The NIF, for example, is single shot. We only do one experiment. We fire the lasers once every 4 to 8 hours. That is the time it takes our laser to actually cool because we picked a laser architecture 20 years ago to give us the maximum power available with the best technology at that time, knowing that we'd have to wait 4 to 8 hours to cool. But that's okay, because every experiment that we do is different. And you can remember back to your high school, your college days, being in the lab, how much of a struggle an experiment is. And you're constantly changing things. Every experiment that we do, every target that we shoot is a little bit different right now because we are trying to learn. On the right, an IFE power plant, on the other hand, would repeatedly shoot the same target over and over at over 10 hertz, 10 times per second. And so there's a lot of development that needs to happen there. To shoot at 10 times a second, you need the lasers that can heat and compress the target to those conditions at that rate. The target factory, at 10 times a second, this is nearly 1 million targets a day that you would be shooting. So we need to be able to produce high volume, low cost, high quality targets very rapidly. You would have a fusion chamber to recover the fusion energy through the energetic neutrons that come out, and then turn that into heat through your steam plant. So the NIF right now, though, does provide us a very unique opportunity to experiment at full fusion scale. But there are yet many outstanding technical questions that need to be solved to make IFE a reality. And these are the IFE technology gaps and challenges. And every fusion approach can and should put together one of these for you to look at. But these are the high-level gaps and challenges we still need to solve. But I also think of them as enormous opportunities and ways that we can involve a larger community. So with the laser driver, we need to develop a more efficient laser, as in turning energy from the wall into laser energy. We need to be able to inject those targets at 10 times a second. The final optics of the laser that turn the laser into the chamber, they have to have high survivability, high damage thresholds. And then there's many commonalities between inertial fusion and magnetic and other types of approaches. We need to figure out the tritium fuel cycle, recycling and waste, figure out the system engineering that pull together all these different components, et cetera. Now, the advantage is that with inertial fusion, this is also very modular. Each of those different parts can be developed independently and brought together, in large part because your target is separated from the driver by quite a large standoff distance. And so we can also do parallel development, look at different options, and then with that, it is upgradable. Now, I know this might make you a little bit discouraged because there's a lot of work to do. So let me leave you with one of these departing thoughts. So far, the NIF has achieved a gain of 2.3, like I said. We know for an economically viable commercial power plant, we need a gain of about 50 to 100. So there's still a lot of work to do, we'll be honest. However, a self-sustaining plant, a power plant that could provide enough energy just to run itself, only needs a gain of 15. And over the past decade, if you remember that first histogram I put up, we have improved our gains on the NIF by a factor of over 1,000 times already. So we are getting close. And we do think we can get to these gains of 15 on the NIF pretty soon in the next couple of years. So it's a very exciting time in fusion. There's enormous excitement in both policy and technology development. In the US, the White House has come out with a bold decadal vision, injecting momentum into the system and bringing everybody together. There's been over 70 years and over $30 billion of investment that we are building off of. Fusion ignition has been demonstrated, and we're also seeing through the private sector enormous creativity and concept diversity, with over $6 billion in private investment and new private companies popping up every day to add to those 40. So it's a really exciting time in fusion, and we're excited to share it with you.
Thank you so much, Tammy Ma. It's great to hear the details of that achievement, which was significant in it proves the science of fusion and opens up the pathway to engineering a future power plant. So hello, everyone. I am Dr. Melanie Windridge. I'm the founder and CEO of Fusion Energy Insights. We help people keep up to date with developments in the growing fusion industry. One of the things that we do is on our website, we publish news insights articles where we look at the significance of some of the major news stories. So in a similar vein, what we are going to do today is we're going to go on a whistle-stop tour around the world, and we're going to be seeing or hearing about the progress in various different laboratories, and I'm going to highlight some of the main achievements and the significance of those achievements. So starting off, we're coming back to the UK from NIF, and we are going to be visiting JET.
I have great pleasure in formally opening the joint European torus.
Since its first pulse in 1983, JET, the Joint European Torus, has been instrumental in advancing fusion energy, symbolising international scientific collaboration, engineering excellence, and the commitment to harnessing the power of fusion energy. As the only machine in the world capable of operating deuterium and tritium together, the fuel for future power plants, JET has pushed the boundaries of science. It set world records in 1991, 1997, and 2021.
That's good.
That was the best baseline pulse ever.
And in 2023, with its final DT experiments, produced high fusion power consistently for 5 seconds, resulting in an output of 69 megajoules from a mere 0.2 milligrams of fuel. JET has made an indelible mark on the fusion world, operating as close to power plant conditions as is possible with today's facilities. Its legacy will be pervasive, not only for ITER and demo, but in all future power plants, including the UK's STEP prototype power plant, which aims to produce energy for the grid. Now transitioning to play a vital role in understanding the decommissioning of fusion facilities, the incredible achievements at JET have been pivotal in making fusion energy a reality for future generations.
So that clearly outlines many of the achievements on JET. Some key ones being the world record for fusion energy that was produced, 69 megajoules, and then also sustaining a high-performance plasma for 5 seconds. These are significant because it shows that we can reliably create fusion plasmas using the same fuel that we would use in a commercial fusion power plant. So from there, we're heading over to France to visit ITER.
Welcome to ITER. In the past 2 years since the last status report, a lot has changed at ITER. In this time in 2022, we had just put the first vacuum vessel sector module into the tokamak pit. And shortly thereafter, we found that we had some repairs to make on major components. The vacuum vessel sector modules on the edges field joints had some geometric nonconformities that required remachining. And the thermal shield, the thin piece of metal that goes between the vacuum vessel sectors and the toroidal field coils, had corrosion that could lead to leakage in its cooling pipes. So we decided to repair all of those components. Repairs are now well underway. Many other aspects have moved forward as well. We now have all 6 of the poloidal field coils assembled. We have all 19 of the toroidal field coils arrived on site. And the central solenoid, we have 4 modules, and that is being assembled on site as we speak. This week, while you're having your FUSION24, our council is meeting to decide on a new updated cost and schedule baseline. So that's the ITER status.
So it's great to see the construction progress at JET, and always impressive to see the images of everything coming together. So you can see the significance here is that ITER is an incredible feat of engineering, and it's really pushing suppliers to new levels and to achieve new things. It's also gathering a lot of know-how, and as Pietro Barabaschi calls it, the know-how not. And this is going to be really important for informing development of future experiments and plants. So from here in France, we're heading to Germany to visit Wendelstein 7X.
I'm standing here in the Taurus Hall, right in front of the experimental stellarator fusion research device Wendelstein 7X. What is a stellarator? A stellarator, unlike its cousin the tokamak, is not based on a strong current running in a plasma to generate the magnetic field for confinement. One big advantage of the stellarator is that it can run continuously. We call it steady state. The big question is a stellarator an option for a fusion power plant? And that's exactly what we want to prove with Wendelstein 7X. Wendelstein 7X is the biggest and most advanced stellarator worldwide. Since the first plasma in December 2015, the device was systematically upgraded and completed. During the most recent upgrade, Wendelstein 7X was equipped with a full coverage of water-cooled in-vessel components. Last year, we reached an important milestone. We reached an energy turnover of 1.3 gigajoule, which is a new record for Wendelstein 7X, and we could maintain a hot plasma for 8 minutes. This fall, we are starting a new experimental campaign. During the coming years, we plan to extend the energy turnover to 18 gigajoule, which corresponds to half an hour of stable plasma operation. And we know if we can do it for half an hour, we can do it forever.
So great to see experiments progressing well at Wendelstein. The main achievement there, as you heard, is the energy turnover of 1.3 gigajoules and the fact that they could hold this stable and hot plasma for 8 minutes. So again, significance getting closer to power plant relevant steady state operation on the stellarator. From Germany, we're heading over to Asia, and we're going to China to visit East.
Institute of Plasma Physics, Chinese Academy of Sciences, is the Chinese fusion research base. It aims to solve the problem of unlimited and clean new energy for human beings and has designed and developed the first fully superconducting tokamak. In 2023, EAST achieved a new milestone of 403-second steady-state high-confinement plasma, which is of great significance for exploring future fusion reactor frontier physics issues and enhancing the economics and feasibility of fusion energy. In the same year, the joint EAST-ITER team carried out physics experiments on the EAST device. The experiments demonstrate the key scientific questions to support and refine the physics research program for the next phase of ITER. After the 2024 experiment, EAST will be upgraded in in-vessel components, auxiliary heating systems and cryogenics to achieve the new physics missions. In support ITER, CFETR operation with full metal wall and vaporization. ASIP is open to participating in worldwide collaboration and making efforts to realize the shared dream of all mankind.
So the main achievement there is that in China on EAST, they achieved 403-second steady-state high-performance plasma. And this signifies, it verifies the feasibility of steady-state high-performance operation in tokamaks, and this will be relevant for future power plant scenarios. And from China, we're heading over to KSTAR in Korea. . 。  . 。 . 。 . 。 . 。 . 。 . 。 . 。 . . 。 . 。 . 。 . . 。 . . 。 . 。 . 。 . 。 . 。 . 。 . 。 .
. 。 . 。 . . 。 . . 。 .
。
I'm Yong Nam, Director of KSTAR. After we built a superconducting tokamak KSTAR without any failures, we continued our research and eventually discovered a new operating scenario, the fire mode, which could stably maintain high ion temperature plasma. Last year, we installed a diverter system using tungsten monoblock in KSTAR. Again, without failures, we confirmed that it was working successfully. We also generated high-performance plasma, maintained it for a long time, and even extended its record in the first tungsten diverter campaign. Now, KSTAR is one of the world-leading tokamak capable of generating high-performance and long-pulse plasma. We hope to share this experience of the success through international collaboration and to learn and further develop the advanced technologies with collaborators. And finally, to realize the dream of infinite energy from nuclear fusion.
And lovely to see there how the upgrade of KSTAR and the diverter has really improved the performance on the machine. So they have achieved, they've held a high performance plasma for a long time, so 100 million degree plasma for 48 seconds, or an H-mode plasma for 100 seconds. And again, this is extending the duration of tokamak plasmas and getting closer to the fusion relevant temperatures and towards steady state operation of tokamaks. And from KSTAR, we're going over to Japan and we'll be visiting JT60 SA.
World's largest tokamak. Challenge. Mission. Experiment. Discussion. Resolution. 5, 4, 3, 2, 1, 0. Achievement. Solidarity, responsibility, coordination, team spirit, ambition, fusion.
Getting ahead of myself there. So yes, JT60, they achieved recently first plasma on what is now the world's largest superconducting tokamak, and they will be testing the high performance plus sustained performance. So we look forward to future results from JT60 SA. Now we're going back to America and we're going to hear from Andrew Holland at the Fusion Industry Association about what's been happening in the private sector.
I'm Andrew Holland, the CEO of the Fusion Industry Association. Thank you for the invite to speak with you all at FUSION24. I'm sorry I couldn't be there in person, but make sure to say hi to Tris Denton, FIA's UK Director. Today I'm going to bring you the latest groundbreaking developments from the fusion energy industry over the past 12 months. The FIA is the unified voice of the private fusion industry, working on regulatory affairs and public policy, can also identify some real advances in these areas that will make the pathway to commercial fusion energy smoother. We've seen Germany, the US, the UK, Japan, and the European Union move forward on new public-private partnerships to advance fusion. And we've seen the UK confirm its regulatory structure for fusion energy, while the US approaches the end of a rulemaking that will also confirm fusion as separate from nuclear fission regulation. Now I'm going to talk about some of the commercial fusion companies that have made significant strides towards making fusion energy a reality. While this does not cover all of them, let's dive into the most exciting breakthroughs of the last year from some of our industry leaders. First, Commonwealth Fusion Systems continues to push the boundaries of fusion technologies in Massachusetts. Their latest video showcases fresh advancements in the dramatic splitting of their vacuum vessel, highlighting the cutting-edge work happening at CFS. Next, First Light Fusion, based in the UK, has also made impressive progress with their unique approach to inertial fusion. They successfully fired a record-breaking shot on Sandia's Z machine in New Mexico, reaching an unprecedented 80 trillion watts. Additionally, First Light achieved a major milestone in their fusion power plant design, overcoming a significant engineering challenge with their standoff distance technology. General Fusion, out of Vancouver, Canada, is making significant advances with the launch of Lawson Machine 26, LM26, in August 2023. This is a new magnetized target fusion demonstration machine designed to fast-track the company's progress to transformative milestones for the next phase of commercialization, achieving fusion conditions of over 100 million degrees Celsius by 2023 and significant break-even equivalent by 2026. This machine is the culmination of over 20 years of building and testing fusion prototypes at the Canadian labs. The plasma injector, a core component of this machine, is already operating and exceeding performance targets. Helion Energy in Washington has been optimizing their fuel cycles and forging significant partnerships. Their recent agreements with Microsoft and Nucor mark a critical step towards commercial fusion energy. Additionally, their focus on creating field reverse configurations, called FRCs, in their fuel optimization tests is a promising development. Kyoto Fusioneering out of Japan is pioneering advances in R&D to empower global fusion developers with innovative engineering solutions. In the last year, they've partnered with Japan's national labs and manufacturers to deliver high-performance gyrotron systems globally. They are installing Unity 1 at their Kyoto Research Center to innovate the fusion thermal cycle and are collaborating with a leading manufacturer in vacuum pumps to pioneer fuel cycle solutions. Kyoto Fusioneering has also forged partnerships to advance fuel cycle development with CNL and KIT while continuing their work with the UKAEA. NearStar Fusion, a startup in Virginia, has made dramatic improvements in their magnetized target impact fusion approach. Their advancements include simpler projectiles and more energy-efficient operations. TAE Technologies in Southern California, in collaboration with Japan's National Institute for Fusion Science, announced the first ever measurements of hydrogen boron fusion in a magnetically confined plasma, a milestone in their mission to commercialize fusion power using hydrogen boron fuel. Tokamak Energy from Oxford achieved a plasma temperature of 100 million degrees Celsius, the highest in a privately funded spherical tokamak. Their superconducting magnet system passed significant cryogenic tests, and they developed a new laser measurement technology for plasma control. Finally, Zap Energy reached temperatures of 37 million degrees C with their Fuse machine, demonstrating the potential of their sheared flow Z-pitch approach. These breakthroughs and more showcase the incredible progress in the fusion industry, moving us closer to a future powered by clean, sustainable fusion energy. Follow the FIA for more updates from these and other member companies.
So a whole host of achievements there from various private companies. But what I'd like to highlight particularly is the movement that we're now seeing from governments. We're seeing the regulatory frameworks being set up. We're seeing fusion strategies and the establishment of public-private partnerships. All these are going to lay the foundations for fusion's success. So I hope you've enjoyed this whistle-stop tour around the various labs. I should remind you that we at Fusion Energy Insights actually have written about many of these different achievements that we've talked about today. So if you want to get a deeper dive into some of the significance, then do head over to the website at fusionenergyinsights.com. And now I'd like to welcome Tammy and Valerie Jamieson back to the stage for some questions.
Yeah, Melanie, thank you so much for that breathtaking, truly breathtaking tour around the world and for your analysis and insights as well that you provide. So let's open the floor to audience questions. We have some roving microphones, I believe. Brilliant, we have some roving microphones at the back. And to our online audience as well, if you would like to ask a question, there's a Q&A box next to your viewer. If you don't want to be in the limelight and you're here in the audience, then you can use the app and that Q&A box as well. So, do we have any questions for Tammy or Melanie? So, yes, please. It'd be great if you could stand up because it's quite difficult to see you from there.
Sure. Hello, can you hear me? Okay, perfect. Thanks, Melanie, and thanks, Tammy, for those excellent talks. My question is for Tammy. What is next for the National Ignition Facility? Seems like a really big breakthrough. Where do you go from here?
Yeah, so, as I mentioned in the talk, a gain of 2.3 is not good enough, either for fusion energy or for some of the science experiments that we need to do. So over the next couple years, we do need to do a sustainment of the facility. It is now over 20 years old, even though it still looks like it's out of a sci-fi movie. If your refrigerator's been running for 20 years, it's time to do some upgrades. And then we are working with the US Congress to get funding to do an upgrade to go to higher energy and higher power so that we can also push up the energy gain. So that is our plan over the next few years. And I'll just mention that the NIF is a open facility where we allow academics, people worldwide to apply to come do experiments through discovery science as well. So if that sounds interesting to you, please do put in an application and we'll help you get experiments done.
Thank you, Tammy. Any more questions in the room? Yes, we have one here.
Hi, I'm Robbie Scott from the Rutherford Appleton Laboratory. What do you see as the biggest challenge in going from energy gain on NIF to inertial fusion energy with lasers?
Thanks, Robbie. So many of those technologies that I mentioned, we do need to put more investment into developing. You can see that with IFE, we took a slightly different stance from MFE, where we said, let's demonstrate ignition and scientific gain first. And now we need to do a little bit of catch up on the engineering side to figure out how to manufacture those targets, figure out exactly which walls will work best with what kind of geometry. And so that research will need to continue.
Thank you, Robbie. Do we have more questions in the room or nothing online yet? Tammy, can I ask a question? Just sticking with you. Tell us about the targets, because I always thought that NIF was incredibly complex because of the lasers, but hearing you talk fairly recently, the targets are incredibly complex too, aren't they? What are the prospects for them?
That's right, yeah. The targets are exquisite pieces of art. Almost. So that little capsule that I showed you that is 2 millimeters in diameter, it is one of the smoothest things humans have ever built on Earth. We try to avoid any little bumps, any little divots on the surface, so it's super smooth, because when you are driving in that capsule at hundreds of kilometers per second, any bump, any divot grows into a mountain or a ditch that just pushes into your fuel and will actually create mix and quench your burn. And so enormous research, both in the US and in Europe together, have gone into developing these super smooth capsules. The target whole ROM itself, that canister, is built in multiple parts. There are many different temperature sensors all around the capsule. And so right now it does take us several months to build one target that is good enough to shoot on the NIF. And so you can project ahead to, if you're shooting 1 million targets a day, the kind of processing and manufacturing we're gonna have to figure out to make these targets robust. But a huge opportunity.
Can I ask a quick follow-on question? Do you think you would have a target factory at a power station to make them there if you've got to make that
Absolutely,
many?
yeah. And so that also has to be folded into the economics, right? It takes energy to run your target factory as well. But yes, your target factory would probably be right next door to the fusion engine itself. And then the tritium that you would breed in the walls, of course, needs to get pumped out to the target factory to put into your capsules. So you want everything on site. But we envision, and similar to magnetic fusion, that an overall power plant would have a footprint similar to fission power plant footprints today, including all that.
And presumably, Melanie, you're very excited at the private fusion initiatives, which are using more simplified targets. So I'm thinking of, say, First Light Fusion, where they have a much simpler approach to creating their targets as well.
I'm not entirely sure about how simple their targets are, because that's excuse me, where all their intellectual property lies. So they've got amplifiers and things in there so that they can change a one-sided shockwave, if you like, into a spherical compression. So I'm not sure how they're going to go about creating all of that. But I think it's really interesting to see different approaches and trying to dispense with some of the engineering challenges in some of the bigger, more well-researched approaches. I mean, we know that there are lots of different challenges, and so I think people are just sort of picking the challenges that they want to go for, because there are some of them on the tokamak side, on the laser side, are still quite formidable, and so there are companies looking at ways of circumventing those. But then, of course, the physics is much further behind there, so there's a lot of work to do on the physics side. So there are challenges in all the different approaches.
Are there any more questions in the room?
Hello, Dan Chambers from Blink Films. Thank you so much for the talk, for the roundup. My question, and it's really from the point of view of public dissemination of this, is how realistic is it to have achieved commercial levels of energy production in the next 14 years?
How realistic is it? Well, from the NIF standpoint, how long do you think it's going to take you to get to commercial levels?
So for the NIF, we do plan on, or trying to push up to much higher gains over the next couple years. Of course, it is science, so I can't give you a prediction for when exactly that will happen. In terms of, building a full power plant, the actual commercial plant piece of things, it very much depends on overall investment and overall will. And it will take partnership between both the public sector and the private sector. And it's very crude, but progress is really measured by the amount of money that goes into the system. But we do realize there's other issues we need to start solving now. We don't have enough workforce to actually bring up the entire ecosystem. And so you'll see that the UK has enormous new initiatives to train huge numbers of PhD students, but not only in physics, in every field. And then likewise, all over the world, we realize what skill sets we will need for the future, and we're trying to invest in that now so that we can try to meet, our 2030, 2040 goals worldwide.
I think it's all about parallel working now. So all of those different strands, and in fact, everything that's being covered at this meeting, in fact, is all of those things need work in parallel so that we can progress all of those together. A lot of the private fusion companies, they're targeting achieving first electricity to the grid in the 2030s. But like Tammy says, it's going to take concerted effort, and it's going to take funding, and it's going to take action by government. So if all of those things are in place, then progress will be faster than not.
We have a big countdown clock in front of us that is telling us to wrap up. Before we thank Tammy and Melanie again for a fantastic session, I do need to tell you what's happening next. At 11 o'clock, after the coffee break, we'll be hearing from fusion economist Nick Lopez-Cardoso about how that wide range of technical approaches that you just heard about is not confusing. It's absolutely essential to the progress and the speed out and rollout of fusion power plants across the globe. And I'll be speaking to wind industry pioneer Andrew Garrard about the extraordinary growth of the wind industry and what fusion can learn. Plus, there is going to be our second stage is going to be opening downstairs on level 2 with a whole programme of talks. It kicks off at 11 a.m. as well with a panel discussion about the standards and regulations that are going to be needed to ensure that fusion energy gets onto the grid quickly and safely. And our guides will help you find the way down to level 2. So thank you so much for your attention this morning. Please put your hands together and thank Tammy and Melanie Windridge.
Thank you. Thank you.